Hello, I'm Ben Jordan, and I'm going to present fully dynamic Coreset spectral clustering, which is joint work with Peter McGregor and Gregory Schwartzman. The motivation for this work is the dynamic graph clustering problem and whether we could extend our previous static clustering algorithm to support it. In the dynamic setting, our job is to respond to cluster membership queries while handling graph updates. When we say cluster, we mean a collection of nodes that are tightly connected to themselves while being weakly connected to the rest of the graph. We model this problem using an interface that supports edge updates and cluster membership queries. Node deletions naturally occur when nodes lose all of their edges. In the animation, you can see what this looks like. Edges and nodes are added and removed, and periodically cluster memberships are queried and shown. This setup is particularly useful for massive dynamic graphs where individual queries may only concern a tiny fraction of the full graph. Last year, we developed the framework for efficiently clustering static graphs using Coresets. This is where we efficiently sample a subgraph, cluster that, and then use it to label the rest of the input graph. It works by exploiting the link between graph clustering and kernel k-means, and our framework bounces between graph space and kernel space, performing Coreset sampling in kernel space, clustering the Coreset graph in graph space, and finally labeling the rest of the graph in kernel space. It can be argued that we already have a dynamic Coreset algorithm for graph clustering. If you combine the merge and reduce framework of Hensinger and Kale for Euclidean dynamic clustering with the Coreset algorithm of Jing et al. And the analysis of our previous paper, this gives you a merge and reduce style Coreset algorithm for dynamic graph clustering. While efficient in theory, it has to sample Coresets during edge updates, which can slow it down in practice and requires a number of clusters to be fixed. Our goal was to extend our static framework to the dynamic setting by efficiently maintaining and sampling from the static Coreset sampling distribution. This requires reworking the steps highlighted in purple. If we can manage this, then we can use the rest of the static framework to answer queries efficiently. Digging into the static CSC sampling distribution, the core primitive is a sampling tree that exploits input graph sparsity to limit the number of sampling tree updates required at query time. It's actually two sampling trees stacked on top of each other. One is used to sample seeds, F, which then seeds the actual Coreset distribution, G. If you've not come across sampling trees before, they're an efficient way to sample from and update categorical distributions. Leaves represent data points and store unnormalized probabilities, or weights. Parents store the sum of their children. To sample a point, start at the root and flip a weighted coin to select a child, and repeat this until you reach a leaf. Updating the weights of a point and sampling both take logarithmic time. Unfortunately, using the basic sampling tree approach is too slow in the dynamic setting. Due to the nature of F and G, the sampling tree may have to be rebuilt from scratch at query time and during updates, making it no better than just running the static algorithm from scratch. We call the trick we found to overcome this just-in-time sampling trees. The key idea is that instead of storing the raw F and G values, we decompose them into functions of linear, persistent, and query time terms that can be maintained efficiently and don't trigger full sampling tree rebuilds. Here, linear means the term at a parent node is the sum of its children. Persistent terms are linear terms that are modified by graph updates and persist across queries. Query time terms are linear terms that are only used during sampling at query time. Timestamps are used to lazily reset these query terms. As an example, one of our persistent terms is called size and simply tracks the number of graph vertices represented by that tree node. Leaves have size 1, and the roots has the same size as the number of vertices in the graph. Using JIT sampling trees, we maintain the static CSC sampling distribution under graph updates and during sampling, giving us an efficient dynamic data structure with identical theoretical guarantees. To serve as a query, we use our data structure to efficiently sample a Coreset graph, then use the rest of the static CSC framework to label the query nodes. Asymptotically, our edge update time is greatly superior to that of the merge and reduce method, while having marginally slower query time for sparse graphs. For very large sparse graphs where queries are relatively infrequent, this gives a much better trade-off. On a variety of workloads, we observe that our algorithm achieves the best trade-off between update and query time while matching clustering performance. In fact, we had to remove the merge and reduce and another baseline from some experiments because their updates became prohibitively slow. Note the logarithmic scaling on the two leftmost experiments where we did include them. Please refer to the paper for more details, and I'm happy to answer any questions at the poster session or via email. Thank you.